Pre-Calculus, Chapter 1, Definition of a Function and Function Notation. We'll start with our textbook's definition of a function. A function from a set D to a set R is a rule that assigns to every element in D a unique element in R. The set D of all input values is the domain of the function, and the set R of all output values is the range of the function. A representation to help conceptually understand what a function is, which many people find quite intuitive, is called a function machine. There is an input and an output, and the machine takes each input value and converts it to an output value. Earlier this week, one of my Facebook friends showed me this graphic, and we'll look at these values from a function machine point of view. So for this relation in the graphic, if we have an input value of 2, the output value is 6. An input value of 3 generates an output value of 12. An input value of 4 gives us an output value of 20. An input value of 5 gives an output value of 30. And finally, an input value of 6 gives an output value of 42. Now we can ask the question, is this relation a function? The answer to this question is yes, because we don't have different input values for the same input values, which takes us back to our textbook definition, which is that each input value has a unique output value. We'll go into this in more detail a little later in this video lesson. You can use modeling to determine an equation for this relation, if there is one, but we won't do that here. I'll just tell you the equation of the function. The function representing this relation is y equals x times the quantity x plus 1. And expanded, the equation is y equals x squared plus x. And since we figured out the function inside the function machine, we can answer the question in the graphic and substitute 9 for x in the equation. So that would give us 9 squared plus 9, which equals 90. Now we'll look at some ways we can represent functions. We can represent functions verbally, numerically, graphically, and algebraically. A big part of practical algebra skill is the ability to transition between the various representations of functions. An example of a function represented verbally is this: John earns $12.50 per hour. Numerical representations can be made in different ways, but maybe the most common way we see is tables of data. Here we see a table with selected values of hours worked, and on the right, the amount of earnings associated with the number of hours worked. The input values are on the left side of the table, and the output values are on the right side of the table. One thing we need to remember from numeric representations is that our information is limited. The values in the table are consistent with the other three representations, but do not describe all the values in the relation. The values in numeric representations do not account for all the values in the relation. Observation or experimentation gives us numeric representations. Next, graphically. A graph is a sort of picture version of a representation. It's a picture that is dimensionally proportionate or accurate. The red line or ray is the picture that shows the relation between hours John works and amounts of money that he earns. We can see that in this picture or graph, the point 10, 125 from our numeric representation or table is a point on the red line of the graph. And finally, we have our algebraic representation, the equation E equals 12.5h. Sometimes the algebraic representation or equation is called an analytical representation. Now that we've gone over examples of what functions are, let's try to understand even better by considering examples of relations that are not functions. First, for verbally, if we say that John earns $12.50 per hour and John earns $10 per hour, this would not be a function. The reason this does not qualify as a function is that if John works for 2 hours, we cannot know for certain how much John gets paid. Will he earn $20? Or will he earn $25? Not a unique output value for each input value. So this would be an example of something that is not a function. Now we'll look at some numeric representations of non-functions. In this example, for an input value of 1, we have in one case an output value of 11, and in another case an output value of 8. Therefore, this is not a function. Different outputs from the same input value, not a function. Another type of numeric representation is an oval mapping like this one. This mapping is a function because for the same input values, there is a unique output value. Here's another mapping. In this case, for an input value of 2, we get an output value of either 6 or 7. So there is not a unique output value for a given input value of 2. So this relation does not qualify as a function. Now we'll look at a graphical representation of a non-function. This graph is not a function because for some input values there are different output values. This blue line segment is vertical, and this is a use of what we call the vertical line test. The link to the right side of the screen takes you to my brief video lesson on using the vertical line test to determine if a relation is a function. The vertical line touches the relation more than once, so this relation is not a function. This equation, x equals -2, is not a function. An x equals equation is the equation of a vertical line and is therefore not a function because it fails the vertical line test. Here's another example of an equation of a non-function, and this is the equation of a circle. Y equals plus or minus the square root of quantity 9 minus x squared. The plus or minus gives this equation away as a non-function. This is the graph of that equation of the circle with a radius of 3 units. We can see that this circle fails the vertical line test because the vertical line touches the graph of the circle more than once. The vertical line test can be used to test all functions, but functions that are verbal, numeric, or algebraic need to be converted to graphs first. Now on to function notation. In two-variable notation we have the equation y equals x squared plus 11x plus 18. This notation with the x and y as variables that we are very familiar with, I call standard two-variable notation. The y, or variable by itself, is called the dependent variable because the value of y depends on what the value of x is. To indicate that y comes from the function acting according to what x is, we can use function notation. Function notation was invented by the French mathematician Alexis Clairaut and the Swiss mathematician Leonhard Euler. So to rewrite the two-variable function in function notation, f of x equals x squared plus 11x plus 18. Again, to emphasize, this part on the left side of the equal sign is pronounced f of x. F of x is the most commonly seen version of a function's dependent variable, but sometimes you may see the notation as g of x or even h of x. It could be other things as well. This concludes our lesson on this topic. There are a couple related videos, one on the vertical line test and another called One Thing Depends on Another, a music video that addresses this topic. This has been Precalculus Chapter 1, Definition of a Function and Function Notation. Thanks for viewing.